Good afternoon, and welcome to today's webinar, PFAS in the Environment, the International Perspective. My name is Michelle Dixon, and I am the Program and Development Director for the Massachusetts Breast Cancer Coalition. I'd like to thank you all for joining us today. I'm very pleased to welcome today's speaker, Dr. Rainer Lohmman. Dr. Lohmman is a professor at the University of Rhode Island's Graduate School of Oceanography. He has an undergraduate degree in biochemistry, a master's in chemical engineering, and a doctorate in environmental science. Dr. Lohmman is also the director of the URI-based Superfund Research Center on PFAS called STEEP, in collaboration with scientists from Harvard University and Silent Spring Institute. MBCC is proud to serve as a community partner on this project. Dr. Lohmman, welcome.
Thank you, Michelle. So thanks for hosting me. I'll have beautiful slides for the next half hour or so, talking about PFAS some more. And I thought because of the timing, most of you will hopefully enjoy a nice healthy lunch. And then if in the worst case, you'll just have a good snooze. In the best case, I'll share something important. So it's actually worth your lunch break. So a few themes I want to touch on. A very quick background on PFAS. I think by now most of the listeners will be very familiar with them. I'll talk to some degree about PFAS in the marine environment, the different animals that we find them in, the spread of them across the environment. I'll touch a little bit on their links to humans, and then I thought I'll finish with an idea that was developed almost slightly over a year ago on the idea of using the concept of essential uses to curb the production and use of PFAS. And it seems to have gotten more traction in Europe than in the US, but maybe that can change. And then a few thoughts at the end. So as Michelle already mentioned, I'm directing a Superfund research center called STEEP, the Sources, Transport, Exposure, and Effects of PFAS. And the partners are scientists from Harvard University, both from the medical school and the engineering school. Silent Spring is our community partner on Cape Cod, and we work with MBCC very happily there. And then we have a range of scientists and outreach experts from University of Rhode Island. And this whole center has 4 science projects that are shown on the top here. It's all shown at www.uri.edu/steep. And there's a transport and fate of PFAS in the groundwater of Cape Cod and fingerprinting of it. There's a project that looks at the childhood risk of PFAS exposure and how it affects the immune system. There's a project that looks at the metabolic effects of PFAS in rodent models and in bioassays. And my own project looks at detection tools of PFAS. And then we have a core that looks at the development of trainees. Those are graduate students and postdocs. Project that works on research translation, provides outreach materials, works on our website. And of course, where most of you might have seen Steve is through the Community Engagement Core, where Laura Shader is our co-lead on the Cape, and Alison McCann here at URI, and an administrative core. So that's kind of what Steve does with respect to PFAS. PFAS, as a quick reminder, are very challenging compounds. We know we have hundreds of contaminated sites across the US, and by now we know those cover from sites where PFAS were produced, where industry used them to make certain goods, a lot of fire training sites, airports. We also have learned over the last few decades that basically everybody is exposed through different pathways. High exposure normally goes to contaminated drinking water, but also everyday exposure through consumer products, dust, and diet. We, of course, also now know there's certain health effects that occur at high exposure levels. So those that live in the vicinity of production plants, there's several cancers involved, and there's a much wider range of effects that are prevalent in the normal exposed population, like you and us on the call, and that includes immunosuppression that was certainly shown for children, and there's links to effects on the metabolic system, so insulin resistance, being overweight, and so on. And the physics and the chemistry of PFAS is very different from traditional pollutants. which is also why they're so happily used by industry in all kinds of applications. They repel water, as is shown on this slide here. They repel oil, so they're dirt repellent. So they can be very useful from a applications point of view. But of course, there's a cost to their magnificence. And there was already some action, a little too late, but nonetheless, EPA made industry switch out PFOS and PFOA, but instead other chemistry have been used. So we haven't got rid of the problem of PFAS, we just changed the prevalent compounds we're concerned with. They're very unusual for PFAS that there's 2 movies that have been made about them. So to some degree, they're already very famous. Devil We Know, it's a documentary, and we showed it at least once on the Cape. It tells the story of how the C8 study came into action, and it was turned to a motion picture movie with Mark Ruffalo, Dark Waters, which was screening end of last year, and shows a little more a dramatized version of the same story. So it's arguably a very famous class of compounds that have made it into 2 fairly successful movies at this point. And they basically tell the story of Rob Bellot, the lawyer who overcame all odds and was able to successfully sue DuPont and get money and compensation, as much as compensation can be appropriate for people who have been contaminated. Maybe a big question that was coming up in the movies is also this question of should we have known earlier? And of course, depending on who you are, there's different answers, EPA versus industry versus academics versus the general public. So from an analytical chemist point of view, it would have been very difficult because all the instruments we had that help us detect the problem of PCBs, of DDT, of dioxins was always a gas chromatograph. And there's one shown here. And they really work well for those compounds, but they do not work for PFAS. So analytically, they were basically hidden from detection for a long time. That changed in the last 20 years or so when liquid chromatography, which you need for these compounds because they're water soluble, so PFAS can only be well separated on a liquid chromatography, and they only became good 20, 30 years ago. And so now we're suddenly able to detect these target compounds at very low concentrations at this parts per trillion range. And that certainly was the basis of being able to come up with health advisories or maximum contaminant levels that are in the single parts per trillion. And more recently, there's all these capability of looking at non-target compounds, so compounds we don't actually know what they are, but just because they show up in the instrument, and you can make clever guesses of what it could be. And that's how some of the newer compounds have been detected, let's say Gen X or varieties of these new PFASs. And basically now, any compound you get into a mass spec, you can get some idea of what kind of structure it might have. And then if you are able to get an industrial standard, you can verify that. And we see more of that happen in the last few years. So there's one exception, and if anybody who's seen the movies, it's clear that on the industrial side, the capability of detecting PFAS was much better developed, and they did know that the compounds were escaping the manufacturing process. So there was a lot of knowledge on the industry, but it wasn't passed on to EPA, so the action was very much delayed. But on the academic side, it was indeed difficult. All right, so quick word. I've talked about this nanogram per liter range, or the PPT. It's the same parts per trillion nanograms per liter. It's not very much, and it's basically we're looking at 10 grams of table salt. If you dissolve that in an Olympic-sized swimming pool, that gives you the nanogram per liter range. So it is a very low concentration, but that's the kind of level we have to measure at to detect them at concentrations of concern these days. All right, so EPA so far has looked and has made a lifetime health advisory limit for 2 PFAS, PFOA and PFOS. Those are the ones here in black. Several of the Northeast states include a couple more compounds. There's sometimes 5 or 6 involved, like the ones in blue. So a little short or longer chain. The Air Force looks at a total of 18 compounds, and the overall family comprises several thousands. And the sort of simple story is we know a lot about very few PFAS, and there's a lot of PFAS where we don't hardly anything about them. We don't know how prevalent they are, what risks they pose, and so on, but it's basically an ongoing story, and there's unfortunately a lot more out there than we know right now. All right, moving on to where we find them. So there's two interesting families within this family of PFASs. There are those that we call perfluorinated, so all the hydrogens have been replaced by fluorine, and they really don't break down naturally. And you have to use very extreme conditions in engineering systems to break them down, be that through UV radiation, through high temperatures, or through strong catalysts to achieve some breakdown, but that's very unusual. So perfluorinated, as far as we're concerned, are forever chemicals. Some of these compounds have some hydrogens involved, and so those can break down. We call them precursor compounds because they break down, and then the precursors become perfluorinated compounds, so then they're stable again. Some of these polyfluorinated compounds, and some are even in fluoropolymers that could be used in carpet coatings, they can be cleaved off over time. So there's a loss process over time. And these precursors, some of those are volatile, so they easily escape into the atmosphere, be that in the house, in a factory, get transported outside, and then they can actually move with the atmosphere around the world rather quickly. And we think that is one of the main reasons why PFASs have reached the very remote, pristine regions these days. And this is shown here in a little simulation. Shown here in blue is the southern hemisphere, and light blue is the northern hemisphere. And then you see in red production areas and emission regions of North America and China. And they lead to an elevated concentration of some of these precursors in green here across the entire northern hemisphere. And that means they have the potential to be transported all the way to the Arctic. And that is then fully in line with why we see that in some animals, shown here as concentration of PFOS in liver. Liver is often the target organ. There's very little in the southern hemisphere, but once we get to the north, we see high concentration in harbor porpoises, high concentration in seals, and really high in polar bears. Now, of course, some of these are top-level predators, so they accumulate contaminants that they eat from their prey. So the polar bear might feed on seal, which might feed on cod, which might feed on small fish, which might feed on zooplankton. And at every stage, there's increase. But the point is that even for an animal living in the Arctic, there is sufficient PFOS and other PFASs around that they accumulate to really high levels. So that has been a lot of cause of high concern, and arguably it was one of the reasons why 3M decided to stop producing the PFOS at the time. And yes, the polar bears, they already faced the problem of decreasing ice, so now they also have the problem of having a pretty nasty pollutant cocktail in their bodies. The interesting things we see in Arctic food webs, and there's a summary here for the polar bear on the left and for the Arctic fox on the right. The concentration of PFOS in that polar bear has actually decreased after the early 2000s, and that is coincides roughly with the time that 3M decided to get out of producing PFOS and the precursor. And that has actually worked. We see that in polar bears, PFOS started to decrease, but we see that for all the other PFAS, so the carboxylic acids and the Arctic fox, for example, we just see a steady increase. So even though we have had some change in industrial manufacturing, we see only a somewhat minor effect as wildlife in a remote place is concerned. And if we look at water samples from the same Arctic region, that was a study we published several years ago. The key part is that the top layer in each of these four plots is surface water, and we think that is entirely supplied by atmospheric deposition of contaminants. And so this atmospheric pathway still is very powerful in the early 2010s. We see very little movement of contaminants through the ocean itself. We can just about barely see it in this one water sample taken close to the Atlantic Ocean. So the main story is the Arctic Ocean still receives atmospheric PFASs, and it continues to contaminate that region. An interesting side story that Elsie Sunderland's group, part of the STEEP project, discovered was working on the Faroe Islands, where they have a history of also hunting and eating pilot whales, and shown as a pilot whale here. Pilot whales, for some reason, cannot metabolize this particular fossa. It's one of the precursors. And so if you look at the pilot whale data, you see PFOS increased over time, PFNA increased. So most compounds decreased. Only the fossa, the precursor, decreased. And that was when basically 3M decided to opt out of its production. And so this trend we can see very clearly. And it turns out pilot whales feed on squid, and in squid you see this trend. And it translates down to a wonderful story that, yes, fossa was a big player. It increased to the early 2000s, and then as production stopped, it decreased very rapidly. So to some degree, you could say it's actually a success story. We realized there was a bad product, we phased it out, and concentration started to decrease. PFOS itself, unfortunately, is on a very slow increase. All right, there's a very recent study also looking at marine mammals, a wide range of them. It was published earlier this year from killer whales, seals, polar bears, dolphins. And the study compared animals from different locations. And the key part here is this one. They had a few animals off the coast of North America and then some from the Baltic and around Greenland, Iceland. And the authors both looked at the target compounds, so all the PFAS that we know we are concerned with, but they also looked at all the other unidentified PFAS. So they looked at the total fluorine that was present. And anywhere there's a barcode in red is basically the unidentified, where they don't know what it is. And all the animals that were analyzed that have lived off North America had a significant fraction of what we call unidentified organofluorine. So we don't know exactly what it is. We know it's some carbon-fluorine bond, so we know it's not really natural, and the target compounds only comprise a small fraction. And that seems pretty unique to the samples of North America. There's other samples from Iceland or West Greenland where there's basically none of this unidentified organofluorine. So for some reason in the US, in our emissions, there's a lot of different chemistries. And of course, that is of concern to us. We see something similar in a range of birds that were collected by a grad student of mine, Anna Robock. She took some samples of Stallwagon National Bank, so off Cape Cod, basically in Massachusetts Bay, some in Narragansett Bay where we live, and then some from the Cape Fear, which you know is a fairly contaminated estuary where there are some PFAS production facilities. And the main story is that she finds two major new products in these birds. These are shown here. They have some fancy names, but the main point is that these are naphthalene byproduct 2 is a byproduct in the production of naphthalene, which is used as a membrane. And included in this naphthalene byproduct are these ether links, these oxygens. They were meant to change the characteristics of the chemistry, but from what we see, we find them in a wide range of birds, particularly from the Cape Fear, and they're a little lower than PFOS, which is the worst chemical, arguably, but at 25 to 50% is not that much better. So the new chemicals bioaccumulate in birds, so that's not a good sign. The top graph shows over concentrations, and the first 10 birds or so are from the Cape Fear, so it's a much more contaminated estuary. That makes sense. And then you see Massachusetts Bay and Narragansett Bay, and we see pretty mostly homogeneous background concentration of these PFOS is present in a wide range of birds. These are mostly great shearwaters that happen to be, that unfortunately ended up as bycatch when fishermen were pulling in their nets. So they were brought back dead to land, and then we analyzed them. So we see they are present everywhere basically, and we start seeing the emergence of newer compounds, which might explain some of this unknown PFAS that were identified in those mammals. All right, I didn't want to spoil your lunch. Moving on to the human side, so this was all on the ecological side, the different bird and animals we have out there. There's a nice summary of us humans being here in the right-hand corner. There's a nice happy family, and the exposure of the industrial chemicals, either through consumer products, be they textiles, food contact materials. These would be applications to enhance the stain repellency of carpets or textiles. And so through that, we get exposed through things we eat, drink, use. Of course, some of these products go to wastewater, go to landfills or wastewater treatment plants. There's application of AFFF, so the firefighting foams, they get back to the environment, and then they can also get back through agricultural use back to us. That's kind of the overall picture, and I want to touch on a couple of those pathways. So this was a study already a few years ago. It was a family in Canada that happened to stain treat their carpet regularly with, and they used Scotch-Guard at the time. I don't think that exact detail of what they used is that important. For some reason, they got concerned about their own exposure to PFAS, so they had the serum analyzed. And this is shown here in the graph on the right. And the key message is the first 5 small entries are all typical concentration of PFOS, PFOA in human blood. And you see they're all in the 5 to 20 nanograms per mil range. And then you see the different members of the family, and you see the concentration increase back to 10-fold. So through their desire to have a very clean and effective carpet treatment, they also managed to dose themselves with a range of PFAS. So those are kind of the warning signs that there's something not going quite right here. There's a similar study that's a little different in design, but the same message. This was again, I believe, a Canadian study. And in this case, the scientists measured the indoor air in a wide range of homes. They measured these precursors here, methyl-TOC and one of the FTOHs, so compounds that can break down, and they can actually break down through metabolism in humans. And then they compared the concentration in the indoor air is on this axis in tiers. So the lowest tier, the middle tier, and the highest tier. And then they compared the concentration of PFOS, this is in this case the metabolized version of MOFOSI, to the indoor air concentration. And in each of these 4 plots, you see as concentration, the air goes up inside the homes, the concentration of the serum also goes up. So there's strong suggestion that indeed this is a causal relationship. If you are exposed to higher indoor air concentration, it'll translate through metabolism in your body that you have a higher concentration of these compounds in your blood. So another warning sign that some of these compounds we shouldn't have in use, and certainly not in our homes. This translates to something very similar to what I've shown you for some of the marine mammals. Here are results of measuring known PFASs. In blue are the sulfonates, and red are the acids, and then black are the unknowns. And similar to the mammals of North America, you see that in the most recent 5 to 10 years, a significant fraction of the organofluorines in human serum are unknown. So these are the black bars, and that's between 5 to 50%. This is in serum of Germans. There's no reason to think that in the US it would be any better, unfortunately. Now, you probably have seen this. This is from the Environmental Working Group. It's a show of the spread of known PFAS contamination sites across the US as a function of time. And it looks like increase in some infection with mumps. And here it goes again. Initially, it was just the West Virginia, the manufacturing plant, but then more and more polluted sites were identified. And of course, as the awareness has been raised and you start looking more, you see more and more. And maybe the best view of this is the 2019 version of this map. Everything in blue is contaminated drinking water. Everything in purple are military sites. And in red are other known contaminated sites across the US. It's worth to point out Michigan, which looks like it has a bad outbreak. And it's just because Michigan tested very aggressively to make sure they identified all the PFAS hotspots in their state. And you can say the same for New Jersey, but also the same for a lot of the other New England states have been looking very thoroughly at drinking water contamination at industrial sites, fire training sites, to make sure that they know to what degree they have to take action. So at the time, Cindy Yu from Harvard published this paper, which pointed out that at least 6 million people had more PFAS in their drinking water than EPA's own advisory of 70 parts per trillion suggested was safe. At the time, we pointed out that we didn't know about small public water suppliers, what concentration they had. We had no idea about private well owners. But based on the available data, we could come up with some guidance of what is making things worse for a water supply. And if you have more industrial sites, it increases your chance of having contaminated water. If there was more military training, fire training in your watershed, that was a problem. Effluents from wastewater treatment plants, and of course, airports all contributed to having a higher chance of having detection. But of course, the other question is 70 parts per trillion actually safe? And that gets, of course, a little tricky. So for now, EPA is only looking at 2 compounds, PFOS and PFOA at 70 parts per trillion. It's a health advisory. Several of the New England states are moving more aggressively. Connecticut, Maine look at 70 parts per trillion, but they include more compounds. Massachusetts is looking at 6 compounds for 20 parts per trillion. And Vermont's looking at 20 parts per trillion for 5. Rhode Island's looking at 20 for 6. So there's some movement on the Northeast region. New Hampshire took a slightly different approach. They established individual maximum contaminant levels for these 4 compounds. But at this point, a court judge ruled an injunction against the legislation or the directive because of a missing cost-benefit analysis. But at the same time, the judge also made it clear that he thought there was otherwise no reason not to keep having those tighter standards. If we go beyond the US, EU, but it is not finalized, is suggesting either a concentration of 100 parts per trillion for a total of 20 PFASs, or, and that will be a game changer, 500 nanograms per liter for total organofluorine. So there's the first time that some entities suggest we should look at all the PFAS together. Denmark, Sweden both look at 11 or 12 compounds. So again, they're fairly aggressive in trying to protect their citizens from drinking water contamination. The US, Canada, Australia are not doing that great. So 70 parts per trillion, it's certainly better than what was there before, but it's probably not protective at it. So the other question is then, and that of course was probably some of you have followed this, there was this famous or infamous case of a Maine farmer who had contamination of a sewage sludge. It made it into into the newspapers. And what we think what happened is that he applied a lot of biosolids, which was then taken up by the grass, was taken up by the cows, and transferred into the milk, and basically he couldn't sell his milk. So we were approached by a couple of journalists from Reuters who sent us 13 milk samples from across the country where in each case biosolids were applied, and they were able to get a local milk sample, ship them to us for analysis. And here's actually good news for a change. These were the extractions, and you see here something in black. This was chocolate milk. Otherwise, you see the separation of the milk solids, the proteins, and then this is the dissolved phase that we analyzed. And the good news is basically in all but one of the samples, we could not detect any compounds above detection limits. And the detection limits were on the between 2 and 10 nanograms per liter. So on the low side, only one of the samples from Michigan had one detection, and that one is actually not even regulated. So the main story is if you drink your milk, keep drinking it, it seems very safe at this point. And how does this link back to the farmer? I think by now it's recognized that he not only used typical normal sewage sludge, but he also had paper and pulp mill sewage sludge, and that probably was the one that had all the PFAS, not the normal biosolids. All right, time permitting, the essential uses idea. So this is a compilation from the Green Science and Policy Institute, all the many known uses of PFAS, and that's a wide range from cosmetics to carpets, textiles, clothing, you name it. And we know a lot of these. And the question is, if they have PFAS, do they really need to be in there? And it actually goes on, the list keeps growing. They're in medical devices, they're in paints, they're in ski waxes, they're in laboratory supplies. So they're all over the place. And are they really needed? Is it essential? So what is essential? And so Ian Cousins, and I was part of that team, came up with the idea of following an approach that was already present in the Montreal Protocol, which was agreed upon to phase out ozone-depleting substances way back when. And in that Montreal Protocol, there was a concept defined of essential use. And essential use is a use necessary for health or safety or the well-being of society. So it's a very high bar. And it's also essential if there's no available technical and economically feasible alternative at the time. So it both has to be essential for society and there's no substitute available. And so based on that, we suggest for PFAS, there's basically the non-essential part. Basically, there is no reason for these compounds or these products to have PFASs. And easy examples are dental floss, water repellent, surface shorts, ski waxes. Then there are those where are substitutable because the substitution is actually available already. And at this point, that includes most aqueous film forming foams and most water resistant textiles. And that same goes for carpet treatment. And of course, then there are those that for now they're deemed essential because they're very important. And that is for some medical devices and some protective gear that, for example, firefighters might use. But again, essential doesn't mean that it has to be permanently essential. It just means there's right now no alternative available. But given research and development, of course, you can phase those out. And so in that original paper, we went through a few more uses and suggest if it is non-essential, substitutable, or maybe essential. And so the most simple, of course, is all the PFAS that are present in cosmetics. There's no real reason, because obviously we have plenty of cosmetics that do not have PFAS, so they can be phased out without any problem. Category 2, something like the outdoor jackets or the tents that have this water repellent. And you can use other PFAS-free compounds to achieve the same effect. They might not be quite as powerful, but they're certainly not as harmful. So they are easily substitutable. And right now, something like the firefighting gear, it's essential. Clearly, anybody wants to fight a fire has to be safe. So yes, if PFAS are involved, by all means, use them. But the firefighters themselves would be very happy if they were able to have gear that also protected them. And the last one, and we often get this question, is my Teflon pan safe? And the simple answer is yes. Once it's made, there's no real harm anymore at home, as long as you don't overheat it. But the problem is that during the manufacturing of the Teflon, there's a lot of emissions, and that's really where the problem is. And the other problem is once your frying pan is outdated, maybe it's all scratched up, what happens to the product at the end of the life cycle? So while industry would like to pretend that Teflon is completely safe, we think you need really to look at the entire life cycle from its manufacturing, where there's a lot of emissions, to the end of life, where there might be again emissions. And that will certainly tip the balance against producing too much of it. I know this is a horrible table, but that was actually the point. This is a new manuscript we just submitted, led by Juliane Glüge, looking at all the available evidence of where PFAS are used. And it turns out there's over 60 categories of uses where PFAS are used right now. So they're very, very, very widespread. So it's not going to be easy to phase them out, but at least within the European Union, this idea of essential use has gained traction, and it's considered in several of the legislation to use that process to reduce the spread of PFAS even further. So I hope you enjoyed your lunch. I think a very simple message is there's basically too many PFASs, too many known and unknown, knowns and unknowns. So it's really difficult if we have to regulate one compound at a time, would always be at the losing end. And there's hope that some other approaches like this essentiality use might help reduce exposure to a larger group. I think it's also clear that once we have been able to clean up drinking water, that we should look towards the next exposure routes, and that certainly includes products that are used in homes and potentially also produce and products like fish or shellfish that might live or grow in areas where there's a lot of PFAS exposure. And for better or for worse, we see marine biota, be that mammals or birds, are pretty good sentinels and to tell us which PFAS we have to worry about. And it's certainly easier to look at livers of birds or marine mammals than to look at human livers. So hopefully using the data from the biota can help us figure out what to worry about next. And I think it may be a very simple point, but the production of chemicals that don't break down is basically just a bad idea because you can't get rid of them easily, and that's not a good thing to do. All right, my time is up. I want to thank everybody who I've had the pleasure of working with. And if there's any questions, now would be a good time. Thank you very much.
Great, thank you. We do have a couple of questions that have come in. The first is, at Joint Base Cape Cod, the Ashamet Pond has PFAS chemicals in the water and in the sediment. So the question is, what are the threats to contamination in consuming the fish or the shellfish for humans?
That is a good question. I cannot give a good answer because I certainly don't know what concentrations are present right now in shellfish or fish from that pond. The other question is what is safe for the consumption of fish, and I know several of the states are working on that. I don't think any state in the Northeast has yet released a guideline of how to handle consumption of fish and shellfish. I think Michigan has a guideline, or maybe New Jersey. So yes, at this point, it seems typically the higher the fish is in trophic level, the more likely we'll have higher concentration of PFAS. So the striped bass will be worse than, oh dear, now I've got to display my fisheries ignorance than some small fish. If people eat from a wide range of different habitats, as in, fish from the Atlantic, fish out of cans, fish from Ashamet Pond, if it's a one-off or you vary it, then I assume it's going to be not a big issue. If you only live off that pond, it would be good to have those fish, shellfish tested and then look at the relative contribution of that input compared to the guidelines we have for drinking water right now. But I don't have those numbers at my fingertips.
Okay. Somewhat related, the question is why there always seems to be the focus first and foremost on PFAS in water contamination. And so the question is that the greatest source of risk to humans versus contamination through the food web?
Oh, good question. I think there's several reasons why the focus is on drinking water. Is one, I think we would all agree that we should all have access to clean water. Mm-hmm. So it's inherently just wrong if it's not clean. It's easier to regulate, and it is certainly a major pathway for everybody, because everything else becomes much more variable, as in not everybody eats fish. Even fish is not the same from everywhere. So everything else becomes very difficult. Sometimes you can go through some market basket approaches of, if people eat a generic diet, what would be their risk? I think in the case of mercury, that's where, of course, fish consumption is the main driver. And then you have basically fish advisories based on that. With PFAS, water has always been the major concern. I think the food web is a secondary concern once you've taken care of the water part. And I don't think at this point we're entirely clear if fish consumption is as bad for PFAS as it is for mercury PCBs. So to some degree, unfortunately, I can't give a straight yes or no, but I'm pretty sure that water has always been a more important concern for exposure for everybody than fish.
Okay, thank you. I have another question for you. Why do you think air emissions regulations are so far behind or less acknowledged in the process, given how much contamination is caused by it?
Oh, good question. I think, well, a little bit of speculation here. Because PFAS were recognized as being water soluble and there was drinking water contamination, I think a lot of the focus initially focused on spreading of PFAS with water. When the science panel in West Virginia put together the exposure pathways, they realized that even there, atmospheric emissions were important. But I mean, to me, that still seems a localized problem. But now, I guess we have learned that even the replacement of P4 Gen X in North Carolina, that was a huge atmospheric emission plume again. So I think to some degree we underestimated that even though these compounds are ionic and they really like to be dissolved in water, they actually travel in the atmosphere readily. So I think that's one part. The other part is the indoor air exposure, and that's, yeah, I guess it's it's just more difficult to regulate because particularly if you have an EPA that doesn't necessarily want to regulate, so that doesn't make it any easier. But yes, you would ideally you would realize that indoor air is an exposure pathway, and you would forbid or phase out any use of PFAS in indoor air products. But that's a pretty aggressive step to take.
I have one last question that's come in. Is there any, can you speak to the development of alternatives? It would seem that, you know, the one path to have PFAS removed is obviously to have an alternative that manufacturers could turn to. Can you speak at all to where we are with looking at alternatives?
Yeah, I mean, there's some progress. I mean, I guess that's the good news of having, you know, creative chemists or scientists or whatever engineers. So if you take the example of carpets, I think the most major manufacturers in the US have by now phased out the use of PFAS as a carpet treatment. So if you now go into the store and buy a new carpet, from what I understand, I haven't tested myself, but they shouldn't have PFAS on them anymore. What exactly they use instead is a commercial secret. I think they are hydrocarbon based. They're probably not quite as good as PFAS in repelling stains, but I think they're pretty good in repelling water at least. So there are alternatives there. I think the same holds for outdoor textiles, rain jackets, tents, and so on. There are alternatives. I think not quite as powerful. The top-end manufacturers have already or have started phasing out PFAS. I'm not sure I'm pretty sure not all of them have. So there are alternatives available. There's even alternatives for the aqueous film-forming foams. I think the latest DoD appropriations bill has basically phased out PFAS for almost all military installations. I think there are some exceptions for aircraft carriers. So even that is possible. And ironically, in that same appropriations bill, the DoD is going to phase out PFAS in food contact materials. So they're actually worried enough about their military men and women that they're going to take that step. Of course, that should ideally apply to the entire population of the US. But that means in all of these cases, alternatives are basically present. And that really shows if you can make strong argument through whatever political action you have, be it through NGOs or through other means, you can force industry to change. It's possible. And in all of those cases, it has basically worked. So as long as we know the key products that we're worried about, and I would assume cosmetics would be an obvious one, you can make that switch happen.
Great. Well, Dr. Lohmman, thank you so much for your time today. On behalf of Cheryl Osimo, MBCC's Executive Director, and our Board of Directors, I want to thank you for this informative discussion. You've given us a great deal of information to think about, and I know that our listeners today enjoyed it. And I would like to thank our listeners for participating, taking the time to join us today. For those of you who are interested, the recording of this webinar will be made available later today on the MBCC website. And I wish you all a very good afternoon. Dr. Lohmman, thank you again.
Thank you.